All right, let's talk about what is, without a doubt, one of the most fundamental yet confusing ideas in all of physics, entropy. It's an idea that explains everything from why your coffee gets cold to the ultimate fate of the entire universe. And to really get it, we need to start with a surprisingly simple question about our own planet. So let's just start with a little puzzle. We all know the Earth gets energy from the sun, right? It comes in as light and heat. But here's the kicker. If we're getting all this energy, how much of it do you think we send back out into space? You might guess we hang on to most of it, but the answer is kind of shocking. It's basically a wash. For the Earth's temperature to stay more or less the same, the amount of energy coming in has to be almost exactly the same as the amount of energy going out. If it wasn't, we'd either freeze or, boil.
And that creates this awesome paradox. If it's a zero-sum game when it comes to the amount of energy, then what is this special thing the sun is giving us that powers literally all life on Earth? Well, the answer isn't about the quantity of the energy, but its quality.
And to figure that out, we actually need to take a trip back in time, about 2 centuries, to the Industrial Revolution, a world of steam, gears, and a desperate need for more power.
So, let me introduce you to Sadi Carnot. He was a French physicist watching Britain just dominate the world with its new steam engines, which, by the way, were only about 3% efficient. So he got completely obsessed with one question: what's the absolute best a heat engine could ever be? And to figure it out, he dreamed up a perfect, idealized engine.
His perfect little engine runs in a 4-step cycle. First, you use something hot to expand a gas, which pushes a piston up. Then you let it keep expanding and cool down. But then, and this is the key part, you have to use something cold to help compress the gas back down so you can start the cycle over. He realized you absolutely must dump some of that heat into a cold place.
And that was his moment of genius. Even in a perfect world with zero friction, you can never, ever convert 100% of heat into useful work. Some of that energy just has to be discarded, spread out into a cold reservoir, just to reset the system. It's like an unavoidable tax that nature charges you.
A few decades later, a German physicist named Rudolf Clausius took this idea of unavoidable energy spread and gave it a name. He called it entropy. It's just a word to measure how spread out or how dispersed energy is.
And this is so important. Not all energy is the same. Low entropy energy is concentrated, it's organized, it's useful, like the heat in a hot iron bar or a fresh cup of coffee. High entropy energy is the exact same amount of energy, but it's spread out and useless, like the waste heat from your car's engine or that same coffee after it's cooled down to room temperature. And this idea led Clausius to one of the most famous laws in all of science, the second law of thermodynamics. He basically said, look, the total amount of energy in the universe never changes, but the total amount of entropy is always going up. This law is why your room gets messy, why things break down, and why time seems to flow in only one direction.
Now that's a huge statement. It explains why our coffee always gets cold. But it brings up an even bigger question. Why? Why does energy always have this unstoppable urge to spread out?
This why question really bugged scientists for a while, until another physicist, Ludwig Boltzmann, came along with an idea that was so simple and so revolutionary, it changed physics forever.
Boltzmann's huge insight was this: there's no mysterious force making energy spread out. It's just a game of chance. It's all about probability. A system doesn't move toward higher entropy because it's being pushed. It just randomly stumbles into the state that is overwhelmingly the most likely. And that state is always the most spread out one.
This little table shows you exactly why. Imagine you have 2 little metal bars and some packets of energy. There are over 600,000 different ways for that energy to be spread out evenly between the 2 bars, but there are only about 90,000 ways for almost all of it to be bunched up in just one of them. The universe isn't trying to do anything. It's just that there are so many more ways for things to be spread out.
And that means something absolutely wild. It is not physically impossible for a cold cup of coffee to spontaneously heat itself up by sucking energy out of the air. It's just so mind-bogglingly, statistically unlikely that you would have to wait trillions upon trillions of times the age of the universe to ever see it happen. So, for all practical purposes, it's impossible.
Think of it like a Rubik's Cube. There's only one way for it to be solved, right? But there are more than 43 quintillion ways for it to be scrambled and messy. If you just close your eyes and make random turns, what are the odds you'll end up with a solved cube? Basically 0.
You're almost guaranteed to end up in a disordered state. The universe is playing the same game, but with an unimaginable number of pieces.
Okay, so this all makes sense for messy rooms and cold coffee, but it raises a huge problem. If the entire universe is on a one-way trip to a more disordered, spread-out, chaotic state, then how in the world can something as ordered, as structured, and as complex as life even exist?
Well, the secret is hanging right there above our heads. The Earth is not some isolated box. We are constantly getting a very, very special delivery from the sun. And here, finally, is the answer to our original puzzle. What the Earth gets from the sun isn't just energy. It's low-entropy energy. It comes in the form of a few very concentrated, high-energy photons of light. For every one of those powerful photons we get, Earth radiates back out into space about 20 weak, spread-out, low-energy photons. We are basically an entropy-exporting machine.
And life is the most beautiful example of this. A plant grabs that concentrated, low-entropy sunlight and uses it to build these incredibly ordered structures, like leaves and sugars. It's creating a tiny pocket of order in a chaotic universe. But to do that, it has to pay that entropy tax by releasing a ton of messy, high-entropy waste heat. So life doesn't break the second law. It surfs on top of it.
This whole cosmic balancing act, creating little pockets of order by making the rest of the universe even messier, it leads to a final, and I think really profound idea about where we fit into the big story.
Think about the very beginning of the universe. It was a state of incredibly low entropy. But kind of like a cup of plain tea sitting next to a carton of milk, it was also very simple. It was uniform, orderly, and not all that interesting.
Now, let's jump all the way to the end, to the universe's ultimate fate, sometimes called the heat death. This is when entropy is at its absolute maximum. Everything is perfectly mixed together, all at the same temperature. And again, it's very simple, featureless. Nothing new can ever happen.
But what about right now? What about the part in the middle? When you pour that milk into the tea, for just a little while, you get these beautiful, complex, intricate swirls and patterns. Complexity doesn't really exist at the perfectly ordered beginning or the perfectly disordered end. It happens only during the transition.
We and every galaxy, every star, every single living thing, we exist inside that magnificent temporary swirl. We're the complex patterns that emerge as the universe unfolds on its grand one-way journey from a simple past to a simple future. And if you ask me, that makes this moment, right now, a pretty incredible time to be alive.